This is Gilad Gour, who will talk to us about classification of multipartite entanglement, which we're all very interested in. Thank you.
Thank you. Yeah, so I just prepared this talk this morning, so I hope it's going to work out well. I would like to talk about classification of multipartite entanglements based on recent work with Nolan Wallach, who is a mathematician at University of California in San Diego. What I'll start with is to show how multipartite entanglement is different from bipartite entanglement. I'll look at just example of maximally entangled states. So suppose we have some n qubits that are in some entangled state, and I will define a maximally entangled state to be a state that any qubit is maximally entangled with the rest. Can define I can also add the requirements that any two qubits are maximally entangled with the rest, and so on. So first question that I'd like to pose is whether such states exist. Well, for 3 qubits, we know that G exists. Is such a state for 4 qubits? Anyone knows a state in 4 qubits? That any 2 qubits are maximally entangled with the other?
I don't think it's possible.
Yeah, exactly. So that's not possible. In 5 qubits is the 5 qubit code state. Here the notation is just the square bracket, it's just a cyclic permutation. So there are 5 terms there in each square. 6 qubits we have that. And by the way, for 5 qubits it's the unique state up to local unitaries. For 7 qubits it's unknown, but I believe it doesn't exist. But I can prove it, but I'm pretty sure it doesn't. And we know it does not exist for 7 qubits. So this kind of some picture of maximally entangled state. But the important part actually is, important set of states are states that are that each qubit is maximally entangled with the rest. So without the requirement that 2 qubits and 3 qubits are.
Is it true that the 5 qubit code state is unique? The 5 qubit code is unique.
Yeah, it's actually it's true that the 5 qubit code state is unique. Even if you take any linear combination in the code space, is equivalent to this state up to local unitaries.
Okay.
It's not trivial, but actually Raines talks about it at some point. So, okay, but how do we classify entanglement? So the basic idea that I'll be talking about here is classification using the idea of stochastic local operation and classical communication. So I'm sure probably most of you know about it. Also, just to emphasize, I will denote here always is there any, maybe I'll take.
There's a slightly longer one here.
Oh, okay. This one? Yeah. Quite long, yeah? So I'll be, when I talk about SLOCC class, I will assume that it's the 2 states can be reversibly converted from one state to the other by elements of this group. SL here is the 2x2 complex matrices with determinant 1. So in the 3 qubit case, we have a simple picture of this classification. There are only 6 roots, but really 3 genuine 3 multipartite entanglement. The important part, though, to mention is that this is a dense set. Most states are here, and this is of measure 0, this class. Or maybe I should have defined what is W and G at this state, but okay, maybe later I think I'll. So to generalize this, I will need one tool from complex algebraic geometry, which is essentially the Kempf-Ness theorem. And I kind of rewrite it here in a slightly different way than it's usually appearing. I modified it for qubits, although we don't really need to assume n qubits. And these are the group G that I'll use, and K is just local unitaries. And we're looking at the Lie algebra of G. And there is a very important set of states, which is, we call them the critical states, because they are critical state with respect to the norm that is induced by the inner product. I'll say in a minute something about it, but they are defined here as the states that the expectation values of all the elements in the Lie algebra is 0. And the Kempf-Ness theorem is just a theorem that connects between the group and the algebra. So it essentially says that every element in the critical state has the smallest norm in the orbit. The orbit of when I say orbit, I mean the set of all states from G acting on phi here on a vector. So the orbit G phi is the set of all these states, and if phi is critical, then it has the least amount of norm. If it's normalized, usually it's 1, so all the other elements has norm greater than 1. The non-trivial part of the Kempf-Ness is really here the third part, which states that the orbit is closed if and only if an orbit of a state is closed if and only if the state is critical. Okay, why this is one simple corollary of this Kempf-Ness is that actually phi is critical if and only if every qubit, if I'm looking at qubits, every qubit is maximally entangled with the rest of the system. And the proof of that is very simple. I'll actually skip it because I'd rather go to some example. So let's look what happens in 4 qubits. What are the critical states in 4 qubits? So we have these two groups, and the critical states are given by this. In this way, it's all the states in A. K is just so up to local unitaries. All the critical states looks like that, and assuming here that it's normalized. What we can see that critical states are not necessarily generic, because a critical state, this can be 0, all those 3 here 0, and Z0 here is 1, so I get this state, which is obviously a tensor product, is something not generic. I won't expect this to be generic. So critical states are not necessarily generic, but nonetheless, the orbit of the critical states, if I look at G times A, so all the states that I can obtain from states like that, this is always dense. And it's dense, it doesn't matter if it's 4 qubits or any number of qubits, or even any number of qubits. The dimension is not relevant. Always the critical states capture almost all states. And we also know that in each orbit, this is in a way the maximally entangled state in the orbit, because of the property that each qubit is maximally entangled with the rest. Any other orbit, any other state in the orbit won't have that property. So that's why critical states are important. But the question is, how can we classify essentially now all orbits? So the focus of what I'll be talking about is how to classify in any number of qubits the set of all critical, the set of, in a way, of all critical states, because each critical state really corresponds to some class of states. Just like the GHZ state. The GHZ state was a critical state, and the W was not a critical state. The reason is because the W, I can shrink it to 0 with an element of G. So the W state, if I just act T inverse 0, 0, this is a 2 by 2 matrix with determinant 1. If I take the tensor of this times 3 on the W state, which is 0, 0, 1 plus 0, 1, 0, 1, 0, 0, then I can see that this is equal just t times w. And so in the limit that t goes to 0, it goes to the 0 vector. So this is why the w is not a stable state. That's the terminology usually that we're using. And critical states are stable states. States that this won't happen because the orbit is closed. Okay, so so the way we classify entanglement, I will show it in a little bit in few more slides. The way we classify it is using SL invariant polynomials. So here, for simplicity, I'll take the qubit case of n qubits. Looking at this group, we define a polynomial that from Hn to C to be, we call it SL invariant when I act on, with G on psi, it is invariant for all G. So here's, just give a few examples. The most well-known example is really the concurrence in 2 qubits. It's given like that, which really is defined in terms of the bilinear form. Actually, the concurrence is the absolute value of this, but I'm talking about polynomials, so this is just a complex number here. I put here, maybe I should say that this vector psi here is defined, if I write psi here in the basis where sigma y looks like in its standard way, just I and minus I on the off-diagonal terms. And so the star here, which corresponds to taking the complex conjugates of the components of this vector, when we write this vector in the basis that that sigma y looks standard. In 3 qubits, for example, there is this hyperdeterminant of Cayley hyperdeterminant, which I think the easiest way to write this determinant is simply by using actually the bilinear form from here, writing this in this way. So every 3 qubit state, I can write as 0 times some non-normalized state, phi is 0 plus 1 like that, and then I can write this polynomial, and this turns to be a G invariant polynomial. So that's a Cayley polynomial. And this, oh, by the way, I'll just mention that this psi 0, psi 1 here, when I do, if I take different vectors, not the same one, like here, I just change it here. So it will be just 0 here and 1 here. That's what appears here. Notice that this actually, the degree of this polynomial is degree 4, whereas the degree of this one is 2. There are no degrees to there is no SL invariant polynomial of degree 2 in 3 qubits. In fact, for any odd number of qubits, there is no polynomial of degree 2. The lowest degree for odd number of qubits is 4. Maybe I'll say something on the degrees later. But here's another example in 4 qubits. This idea of extending this to this works. And for the critical states that I was talking before in 4 qubits, these polynomials look like that. I'll say just a couple more words on this. For 2 and 3 qubits, these are the unique SL invariant polynomials up to just some powers. For 4 qubits, this is not unique. There are the set of all SL invariant polynomial is spanned by 4 polynomials of degree 2. This is the degree 2 one. There are 3 more, 2 of degree 4 and 1 of degree 6. And they together span the whole set of SL invariant polynomials. Now let me say one word why we're interested in SL invariant polynomials. So some reasons why they are interesting, and then I'll say the main reason. First of all, I can use them to define an entanglement monotone. But again, it's not operational, but still, it's something interesting. These are actually polynomial. These entanglement monotones are actually monotones under separable operation, which is a little bit more than LOCC. And they also have this very nice property. If we're just sending one of the qubits through some channel, some noise, then it's interesting to see that this kind of measure, no matter which function you choose here, doesn't really depend. The ratio between the final state after I send one of the qubits through a local noise, divided by the entanglement in the initial state, because these are measures of entanglement, it's only depending on the channel that I applied the noise to. And it's given here by this minimum over all operator sum representations of the channel. The K here is just the class operators. So it's kind of a very nice property that it doesn't matter what is the initial state, the entanglement will always decrease by this amount, by this factor, which is always smaller than 1. And it's given here as the concurrence of the Choi matrix. Phi plus here represents just the Bell state. That's if it's qubit. Of course, there is generalization of this for qubits. And of course, if we have noise like that, it also there is no equality, but at least there is some nice upper bounds. So they have these nice properties, and we can see actually if we have n qubits and n is big, then the entanglement decreases by a lot because each factor here is smaller than 1. And with a little bit more analysis, one can see that really the critical. Oh, I should have said before that. There are other kinds of states like the W states. The W states, those states belong to what we call the null cone. The null cone is the cone of all states that all SL invariant polynomials vanishes on them. There are such states, but it's of measure 0, but it's more than just being measure 0. It's really, really small. The dimension is small for those states. So I'll just point out that everything I'm talking here is not going to apply if this is 0, if I'm taking state in the null cone, because then this will be 0. But actually, those states in the null cone has some property which is nice, that they actually, if we send states in the null cone through a local noise, they decay slower than critical. The critical entanglement is quickly, very quickly destroyed under noise. Okay. One more property, I'll skip it, maybe I'll just say it in just a few words. We can use SL invariant polynomials to define monogamy of entanglement. Here is the tau is a measure of entanglement. Rho, so if I have a bipartite entanglement, psi AB, and rho r is the reduced density matrix, so this is just a linear entropy. I define the tangle to be of a bipartite state to be the linear entropy, essentially, of the reduced density matrix. So if I take this to be the measure, then I can I see that this is the 3 tangle. The 3 tangle is the SL invariant polynomial that I defined in the previous slide for 3 qubits, and it can be given in this way. So there is some relation between SL invariant polynomials in 3 qubits. Also, SL invariant polynomial have some relations to other measures in 4 qubits. For example, if I look at the tangle between A, this system, and the rest of the system, and I look at the average of this, and then I look at the average of any bipartite cut. So then the Kempf-Nest theorem tells us that this equal to 1 if and only if the state is critical. And there is another nice relation showing us that the 4 tangle, the SL invariant polynomial of degree 2, is related to these quantities in this way. So there are some, my point here is just that there is some nice relations. By the way, this equation alone tells you that there is no maximally entangled state in 4 qubits that, I mean, this can never achieve the maximum possible value of 3 halves. This is 3 halves because if I have 2 qubits, this dimension 4, so the maximum value this can be is 3 halves. But the maximum, this equation, this is always positive because it's the absolute value of the SL invariant polynomial of degree 2. And so that tells us immediately that this cannot be greater than 4 over 3. So SL invariant polynomials have some, they play some role in some nice in relation to other measures of entanglement. But the main reason I think to study SL invariant polynomial is to classify SLOCC orbits. And what I would like to show is that SL invariant polynomials can do this job. And then after I'll show that, I'll show how to construct all of them. Now, it's very ambitious to construct all of them, so there will be some caveats to that, but we'll see. So, so I say that two states are in the same SLOCC class if they are related by some element of G. And because G is in SL, I have to normalize the state to make it normalized and put some phase. Now, suppose we have an SL invariant polynomial of degree k, that it's homogeneous. So it's not just a polynomial, but it's also homogeneous. Then if I apply fk on this psi, and suppose that psi is related to phi in this way, then I can factor out this term here and this. And because it's in SL invariant polynomial, the f when is acting on g phi is the same as f acting only on phi. So that's why we have this relation. So we see here, first of all, that SL invariant polynomial it looks like they cannot really distinguish between the orbits because we have these factors here. I mean, so they are not the same for two states in the same SLOCC class. But if you take two of them and you divide them one by the other, so if I have another SL invariant polynomial of degree k, then the ratio between them would be equal. And now because it's essentially the same factor if the degrees are the same. And we've shown in the work with Nolan, we've shown that this is also, the converse is also true. So that's less trivial, that if the ratio is the same and the states are not in the null cone, both of them. I mean, if one of them in the null cone and one of them is not in the null cone, it's very easy to check that they are not in the same orbit. But if both of them are in the null cone, this won't tell us anything. But if both of them are not in the null cone, that's the non-trivial part. This is an if and only if, which means if all SL invariant if all the ratio of homogeneous SL invariant polynomials of the same degree agree on both phi and psi, then the states are in the same orbit. Okay. So now so that's the main motivation why we want to actually study SL invariant polynomials. They're really classifying the orbits. So how do we? So first of all, let's talk about the degree. What type of degrees SL invariant polynomials can have? I should have mentioned that now the G that the operator G here will be as M1C. So M1 will be the dimension. So the Hilbert space Hn consisting of n qubits. And now I'll be very general. Any qubit is in some dimension. I'm not restricting the dimensions, and we have n qubits. The only restrictions that we have is that it's finite dimensions. And the G will be just the tensor of this M of this group. So it's the SL group. So our goal is to really classify these states. First, I'd like to tell you something about the dimension. So what the dimension and SL invariant polynomials can have. There is a very simple argument to show what the dimensions are. Suppose I take some roots of unity psi that satisfies this relation for some j. So that implies automatically that C times I is actually in this group because its determinant is 1. Right? So because of that, if I take an SL invariant polynomial of degree k, and I look at this, I take out, because it's homogeneous, I can take it out. And because it's SL invariant polynomial, because this belongs to G, and so it's G invariant, it means that these are the same, so therefore it means that this has to be 1. And that immediately implies that the degree k of any SL invariant polynomial must look like some integer q times the least common multiple of the dimensions m1 up to mn. Okay? Are you guys following me still? Okay. So before I go to the full construction of all of them, I'd like to start with a simple one. Well, it's relatively simple to see. Something in qubits is very simple, and that is essentially this matrix here. Makes everything much simpler, or sigma y, if we want. This matrix has a very nice property that if I multiply any matrix in SL by this A and the A transpose, it remains invariant under this action. And because of that, we can define, this is really the main reason why this bilinear form, so if I take two vectors in the space of n qubits, and I look at this bilinear form, of course I can replace it with sigma y, but just for simplicity I rather working with J, because then everything here looks with real, there's no complex numbers appearing, because this is the bra and the star here. So this defines a bilinear form, and it's the main thing about this bilinear form, it's G invariant. So if I apply G on both sides, because of that property here, we have that. And that's really the main reason why the degree, the polynomial, why this is, SL invariant polynomial, I will call it SLIP, SL invariant polynomial of degree 2. It's a homogeneous one. That's why these are always invariant. And so now there is a very nice way to actually define many SL invariant polynomials using this inner product. And the way it goes is like this. So let's take n qubits and just take any bipartite cut between. So I'll denote one by AQ. So this is this system. And by B, n minus q. So there are q qubits and n minus q qubits here on this system. And then if I look at this bipartite cut, then any state I can write I take some orthonormal basis uj of AQ, and this is an orthonormal basis of this system. So I'm viewing this as a bipartite state in this bipartite cut. And then it's possible to show, because of the properties in the previous slide, that these quantities here turns out to be a class of SL invariant polynomials. So what are they? It's relatively simple. The A is just this matrix A. The size of this matrix is 2 to the q by 2 to the n minus q. Right? This is this matrix. And U and V are just defined, are just they are matrices that define in terms of the bilinear forms that we defined in the previous slide. So it just define like that and define like that. So it's very easy to see that we can define SL invariant polynomials in this way. So that's very nice and very simple. The question is, are these all of them? In the case of a qubit, that's probably the important question. For degree 2, yes, they are all the degree 2 that there are. Also, all of the degree 4, which is a little bit less trivial to show. But all the degree 4 are of this kind. But of course, there are degree 6 and 8, and they are not all of them. In fact, in 5 qubits, there exists exactly one polynomial of degree 6. And you cannot write it in this way. We'll see it's more complicated. So what I'll do now is move on to define the set of all SL invariant polynomials. How much time do we?
Half an hour.
Oh, half an hour, okay. So, so that's what I'll try to do now, define essentially all of them. So these are kind of new slides, and I hope I'll define. So what we'll do is first, is rather than, the main idea of what we did here is instead of fixing the number of qubits and trying to find all the SL invariant polynomials, we're fixing the degree and trying to find all polynomials no matter how many qubits we have. And that's kind of makes, it's kind of a shift that makes really things much simpler. So again, this will always be our system, and this will be the group we will be talking about. So the first step is to view polynomials slightly as inner products. So we're going to define, because we are interested in degree k of polynomials. So what I will show now is to construct a set of all degree k SL invariant polynomials. We're going to take the degree k, we're fixing it, and we're going to look at k copies of this Hilbert space. And then we're taking x will be the variable. So this is a fixed vector, some vector here. I fix it, and then I look at x, that this will be our variable in Hn. And so I'm going to define a polynomial, which is just an inner product of this fixed vector here with k copies of a vector here. So obviously this polynomial is of degree k. It's degree k polynomials of x. Now, how do you think we can make it? Because I think I'll ask you a question. How do you think we can make this polynomial SL invariant? Like, what we need to require from essentially from that vector, because every vector here corresponds to a polynomial.
You shift x by the action of g and average. I mean, that's the basic intuition to brute force to make it SL invariant.
Right. I mean, if we're going to apply with, when we're applying g to x, so g will come here. Now, because I have k copies of this, so there will be k g's. But then I can apply the g back on this vector instead of on the x. So what I'll require is that v is fixed when I'm acting with all elements of g. Now, I don't need to put a dagger here, because I mean, here, when I move it to here, I need to apply a dagger. But because we're requiring for all g in g, the dagger is also in SL. So that's why we can say that all SL invariant polynomials of degree k can be written essentially as in this way, where the vector v has the property that is fixed, that that when g acts on it, it fixes it remains the same. Now there is some subtlety, but I'll skip it unless someone will ask a question about it. But essentially, the set of all SL invariant polynomials of degree k can be written like that. So they are Fv, where V belongs, this is how we denote the subspace. This is a subspace of this Hilbert space that is fixed under, that every element in the subspace satisfies this equation for all G. So this is a subspace that we'll be working on. So these are the SL invariant polynomials. Now the question is, we didn't do anything so far. All we did is just translated the problem. Instead of looking at SL invariant polynomials, we want to find actually this subspace? How can we find this subspace? So the basic idea is the following. Is what we just, I mean, we were thinking about it for years until we suddenly realized something that is relatively so trivial that actually answered that question. And that is, if you take k copies of this tensor product, it's essentially isomorphic to this space, where it's as if I took k copies of each one of them separately. So in this picture here, all it means, if I denote T, this intertwining map, this isomorphism from here to here, what we are doing is, if we're taking, so we're looking at 3 qubits, or 3 qubits, and the different dimensions, so they have green and blue and red corresponds to different dimensions, then what this intertwining map just does, it just breaks it instead of 4 groups of 3 qubits into 3 groups of 4 qubits. That's all it does. But see how powerful this is. What it does is that now, if I look at G, element of here, how this is acting on this, so it's here, this element G acting on this face in a natural way, just in this way. But how does it act here, on this space? So on this space, it's also under this intertwining map, acts like that. What this means is that now, on each space, it's the same G. It's G1 tensor, G1 tensor, G1 acting on this, and I want to find what the subspace that is fixed under this action now, for each one separately. So that's a tremendous simplification. So instead of calculating this, all we have to calculate now is this subspace of this space, which is essentially all the vectors that are fixed under k copies of H, but it's the H that belongs just to SLM. So
you have a phase for each, a different phase for each term.
A different phase for each term.
I mean, you want the whole thing to be invariant. So if you had a phase for each bit of the way you broke it up, they just have to, the product of the phases has to be 1.
You mean the phase? So, can you ask again the question? Which?
In your final equation, you have it invariant.
Right.
But if it had a phase for each component, for each bit of the thing you've broken up.
No, we actually don't want a phase because we want it to be fixed. Why is that? Because then it's not going to be, where is it coming? It's coming in, well, you don't mean a phase. First of all, this will be in SL, so I cannot just multiply it by any phase. It's specifically, because its determinant won't be 1. And we also know that the degree is actually the dimension m divides the degree. K is actually m times some integer. I don't know if that. So you're talking about maybe just a phase here. So let's see. Well, it's not going to be SL invariant, polynomial. So it will be a polynomial.
The whole thing has to be invariant.
Yeah.
And each subbit doesn't have to be invariant. It's not very deep.
Yeah. Oh, that's a good question. So if we take n copies of it, essentially, Yeah. Okay, I'll have to think about it and see if I'll get an answer later. So, okay. So basically we have this, if I summarize it, and the problem now becomes, instead of calculating this, we want to calculate that. I'm still trying to figure out that vector. Okay. I mean, that's a question actually we anyway, I can't come with an answer right now. So we have to summarize, this is the n copies. And now calculating this is a much simpler thing than calculating this. And in fact, there is standard techniques to calculate it. This, essentially the Schur-Weyl duality, standard techniques from representation theory, which says the orthogonal projection. So the way I'm going to look at it, so first of all, instead of defining the subspace, I'm going to define a projection to that subspace. That's enough. And the projection from here to here is given by this formula here. What is this formula? Sk here is the permutation of k elements. And sigma here is a permutation. So here we're summing over all permutations. So this sum contains k factorial terms. Remember that k, our degree of the polynomial, is always divisible by m. Chi is the character of Sk, the corresponding to particular partition of lambda that is given here, and d lambda is the dimension of the ERAPs that corresponding to this partition. Now, that's why essentially with this formula that we have all the projection, and with this isomorphism, we found out all SL invariant polynomials in any dimensions. What's the problem is, of course, how practical this formula here. Just give. So first of all, if k is equal 6, it's already 720 terms here involving, and we have to calculate all these characters of the groups of permutations. So it's very nice that we kind of identify it, but it's still, of course, it's a very complicated problem. To get an insight into it, let's look at the dimensions. So we could also use these techniques to calculate the dimension of SL invariant polynomials. For example, if I define d of k and n, k is the degree and n is the number of qubits. If I'll use this just for qubits, then the space of the dimension of the space of SL invariant polynomials of degree k is given here. It's given by this formula for degree 2, because as I said, for qubits, if n is odd, then this is 0. And if it's not odd, if it's even, then it's 1. There's only one SL invariant of degree 2. For degree 4, we have this formula. For degree 6, we have this formula. What you can see here, actually, something interesting, that's what I mentioned before. If you put n equal 5, this is equal to 1. There exists exactly one degree 6 in 5 qubits. And then in degree 10, it's getting complicated. With the way we generate this is just some mathematical program that we have, and we can actually get big numbers here. Up to 100, we could get the formula here. But we also were able to show limiting case where k goes to infinity and n goes to infinity, that they are both, this dimension is exponential both in n and in k. So, so that's kind of the bad news. So the good news is we found them. The bad news, I don't know what we can do with that. So because it's getting quite messy. So let me just summarize the main idea here. Again, is that we fixed the degree and calculated all the polynomials of that degree. This does not mean that if we have no, for example, one thing we don't know is if we fix the number of qubits, we don't know how many SL invariant polynomials are there. We only know, what the dimension, that's what I mean, how many. What we do know is that if we fix the degree, then we can calculate the dimension. So that's what we have. So I guess I'll stop here. Yeah. Okay, thanks.
Any more questions?
Is there some form of robustness in this classification? So you classify these orbits under, somehow classify the orbits under SL, under stochastic local operations. But if an experimentalist comes to you and says, okay, I have this state up to those error bars, can you then? Yeah,
then it's changed completely. Then it's not. It's very different. So they have, I don't know if they use something like that in entanglement polytopes, that paper by David Gross, who's here somewhere. But so there I know they have some robustness, like it is useful for experimentalists. But here it's just very. This is very sharp. Like there is no place to. If you change it a little bit, it's changed the whole picture. So there is no.
But you mentioned that you get entanglement monotones. So this would give some sort of partial order at least.
Right. It's definitely all of them are all of them define monotones. But what they also really define is the critical set. So they first of all tell you if you are in the critical class or not. If you find one that is non-zero, you are in the critical class. And then let me show you something about what you asked. It was just in the beginning where I put this formula in 4 qubits. I think that's here. For example, this is something actually interesting. This can be 0. You see, when this gets the maximum possible value it can be, which is the maximum average entanglement, actually this SL invariant polynomial is 0. So if you look at one SL invariant polynomial, it can be 0 even though you have a lot of entanglement. But of course the other polynomials will not be 0. So you have to look at all of them, and that's where the partial order can be defined in this way. But what I meant is if you do some errors, if you kind of if you look here, right? So I'll maybe in the 4 qubit in the critical set of 4 qubits, I think it's easy to see. So if you look here, these are the exact numbers. Now, if I allow for an error, it's a different class. You see, SLOCC class, every different vector here of this. If I take different values for Z0, Z1, Z2, and Z3, then I get a complete different class. Each element here is generating a different class of SLOCC. So that's what I meant, that it's not.
Any other questions? Yes, I should thank Gilad again. Thank you very much.